अस्सलाम वालेकुम and good morning. आज का टॉपिक है ionization energies. Ionization energies is part of the atomic structure chapter in the chemistry syllabus, in the AS level chemistry syllabus. And the accompanying note for this can be found on AurParho.live. And this is what it's called: ionization energies atomic structure. So yeah, so let's begin. First of all, ionization energy होती क्या है? Ionization energy is defined as the energy that you have to input into an atom. वो energy आपको atom में डालनी पड़ेगी in order for it to lose one of its electrons. अगर वो उसका पहला electron है, then that will be the first ionization energy. Second electron will be second ionization energy, and so on. इसको पहले example समझाते हैं. For example, there is a chlorine atom. सही है, this is a chlorine atom and we input energy. हम इस पे energy डालेंगे. See, अब for it to lose one of its electron, so it becomes from a neutral chlorine atom, it becomes a chlorine plus ion, meaning that it has lost one electron. So the amount of energy that we needed to do this is what we'll call the first ionization energy, because this is the first electron. So the electron that was lost right here, this is the first electron that is lost from a chlorine atom in its neutral state. So यहाँ पे ये neutral था, and now it's a plus one cation basically. So this energy we would call first ionization energy. सही है. अब यहाँ पे एक पॉइंट है नोट करने के लिए, ये है कि आप ये नहीं कर सकते, यू कैंट से दैट Cl2 एंड देन मैं इसमें एनर्जी डालूँगा, एंड देन व्हेन दिस Cl2 becomes like 2Cl plus, ये फिर मैं इसको फर्स्ट आयनाइजेशन एनर्जी कहूँगा. दिस इज़ रॉन्ग. सही है, दिस इज़ रॉन्ग. ये इसलिए क्योंकि जब आपके पास Cl2 मॉलिक्यूल होता है तो एंड इट्स ऑलरेडी इन इट्स गैशियस स्टेट, और मुझे इसको फर्स्ट इसके +1 कैटायन में करना है, तो मैं ऑब्वियसली इसमें एनर्जी डालूँगा. जब मैं इसमें एनर्जी डालूँगा ना, सो फर्स्ट इट्स Cl बॉन्डेड टू Cl. तो ये जो कोवेलेंट बॉन्ड है, सम ऑफ दिस एनर्जी जो मैं आई एम अस्यूमिंग कि ये सारी फर्स्ट आयनाइजेशन एनर्जी होगी जो उसको इलेक्ट्रॉन एक्सट्रैक्ट करने में लगेगी, that will be false, because a little portion of this energy will actually go towards breaking this bond. So जब Cl और Cl के बीच में bond टूट जाता है, and then you have Cl and Cl atoms separately, they're neutral Cl atoms, और फिर उसकी जो बाकी energy है, the remaining energy इन दोनों में लगेगी to extract one electron from each, resulting in Cl plus and Cl plus. And this energy is what you can call first ionization energy. लेकिन अगर आप देख रहे हैं इसमें carefully, we really don't know how much of the total energy this is. So इसलिए we always start with neutral atoms, not molecules. And this is because we know exactly how much energy we're putting in, and we are sure that जो भी हम energy डालेंगे ना, it's not going to go towards breaking a bond, it's not going to go towards changing its state of matter. It's going to go only and only towards extracting that one electron to turn it into a +1 cation if it's the first ionization energy. So similarly, एक और example देख लेते हैं जल्दी से. For example, if we have a sodium metal and this is in its solid state, हम जब इसमें energy डालेंगे, these are gaseous sodium ions and these are just the neutral ions that we need. सही है. So ये वाली जो energy है ना, the energy that was required here, this is not the first ionization energy. However, जब हम इसमें energy डालेंगे, when we put energy into the neutral gaseous sodium ion and then it turns into the sodium plus ion, this energy, this we can call the first ionization energy, because we started at a neutral gaseous atom and we just forgot that, and ended up at a positive gaseous cation, and that is what first ionization energy. So formally, first ionization energy is defined as the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of univalent, which basically means +1, positively charged ions. Univalent means a charge of 1, whether it's positive or negative, and then positively charged ions. And that definition is also written in the notes. So yeah, now let's look at trends in ionization energies. So trends in in ionization energies. So yeah, so first we'll look at the trends between successive ionization energies. इसका मतलब क्या है कि how does the first ionization energy differ from, I'll just put versus second ionization energy, and how does that differ from the third ionization energy. अब इसका pattern ये है, I'm just gonna tell you first and then explain it. इसका pattern ये है कि ionization energies increase. So first ionization energy is less than the second ionization energy is less than the third ionization energy. Now why is this? ये इसलिए क्योंकि let's for example just draw quickly a sample atom. Let me pick a element quickly. Let's see, let's draw carbon 2 4. So yeah, let's draw carbon. This is carbon's nucleus. This is its 1 2, and this is too rough. That's better. 1 2 3 4. So this is carbon, and it has 6 electrons. Carbon has 6 electrons. There we go, we've drawn them. So let's say this is a carbon atom, this is a neutral carbon atom, and we put in energy and we remove this. So this was the first ionization energy that we put in to remove one of the most outermost electrons. So yeah, now whatever energy we put in after this to remove another electron will be the second ionization energy. And in this case, जो nuclear force थी, जो nuclear force of attraction, जो positively charged nucleus attracts the negatively charged electrons, ये जो है ये constant रहेगी throughout this entire situation, right? लेकिन electrons के बीच में भी तो repulsion है, and this like inter-electron repulsion जो electrons के बीच में है, this makes it easier to remove, क्योंकि समझो electrons एक दूसरे को धक्का दे रहे हैं, they just want the other electrons to not be there because they're the same charge. So वो एक दूसरे को atoms के बाहर धक्का देने की कोशिश करें. They're trying to push the electrons out of the atoms. Each electron is trying to push its fellow electrons out of the atom. तो इसलिए first ionization energy कम इसलिए है क्योंकि at that point the repulsion between all of these electrons is at its maximum point. So yeah, but when we remove this one electron, सबके बीच में repulsion थोड़ी थोड़ी कम हो जाती है, क्योंकि उनके बीच में उनको ज़्यादा जगह मिल जाती है आगे पीछे हिलने की, राइट? तो जब उनके बीच में repulsion कम हो जाएगी, इसका मतलब we will require to put in more of our own energy to be able to pull out one more electron. So which is why जब हम दूसरा electron निकालेंगे तो that repulsive force जो पहले थी, जो हमारी मदद कर रही थी electrons के बीच में, वो थोड़ी कम हो गई है. तो उसकी to compensate for that हमें थोड़ी ज़्यादा energy लगानी पड़ी है. इसकी वजह से first ionization energy will be less and second ionization energy will be more. And this is the same trend, and you follow it with the third and fourth and fifth ionization energies, and so on. So that was the trend of successive ionization energies. So yeah. And you can also, if you want, you can also understand this in a different way. I'm just gonna redraw this. So there's such a thing as effective nuclear charge, and it's basically this total nuclear force per unit per electron, right? So if there are more electrons, this force per electron is less, and as the number of electrons decrease, like for example we take this out and we take this out, the force per electron increases. So this is called the effective nuclear force. And जब हम एक और electron निकालेंगे, since there is a greater effective nuclear charge on that electron, a nuclear force, greater effective nuclear force, तो हमें ज़्यादा energy लगानी पड़ेगी to remove it. So that's just another way of understanding it. Now let's talk about the shielding effect. Shielding effect क्या होता है? Shielding effect. वापस से हम कार्बन या to correspond better with the notes, हम magnesium के example ले लेते हैं. So this is the magnesium nucleus. This is its duplet. This is its octet. And another shell which has 2 electrons. So yeah, shielding is basically when these, for example, these outer electrons experience a lesser nuclear force or a lesser nuclear attraction because they are essentially shielded by this full shell of electrons and by this full shell of electrons. And in turn, these electrons experience a smaller nuclear force than these electrons because they are shielded by this stable duplet. So basically, shield, as like the farther you go from the nucleus and the more filled shells you have between the concerned electron, like for example, let's say this is the concerned electron and this is the nucleus, the more filled, the higher the number of filled shells. So like this is a filled shell, you have a stable duplet here, like this is a filled shell and this is a filled shell. So as the number of filled shells between the nucleus and the concerned electron increase, the shielding effect increases. Let's relate this to what we just studied about. What did we just study? We studied about the successive ionization energies, right? So let's say we remove this electron and we remove this electron. So yeah, now the next electron that we remove has to be one of these 8. It has to be one of these 8. Now let's say we choose to remove this electron. So we just talked about shielding and we know that this experiences a smaller nuclear force than these electrons, right? So we had to overcome a smaller force, so we required less energy. And now that we have to overcome a stronger force because there is less of a shielding effect, you're coming closer to the nucleus. This shell is farther from the nucleus than this shell. So as you come closer to the nucleus, the shielding effect decreases and you need to put in more energy, which is why in this case the third ionization energy would be so much greater than the second ionization energy. And since we're on this topic, we'll just cover another important point, and that is that when you jump shells, the difference in ionization energies is, relatively significant. Like for example, if you were to remove this electron and say this off the top of my head, this is not an accurate value whatsoever, but let's just say this was 100 kilojoules per mole. See, that was the energy that you required per mole to remove that one electron. And since second ionization energy is greater, let's say this was first, let's label this first ionization energy, and then we removed another one, so there was a second ionization energy and it was greater, so it was 200 kilojoules per mole. Once again, these are example values, they are not representative of whatever atom at all. So the second ionization energy is a bit more than the first ionization energy. Now when you jump shells, so basically now you're going from this third shell to this second shell, because now you have to remove this electron or one of these 8 electrons. So let's say we remove this electron and this is going to be our third ionization energy. And now you'll notice that you went from 100 to 200, but now that you're jumping shells and you're coming so much closer to the nucleus, and the shielding effect is decreasing, right, and the nuclear force on the electron is increasing, so this change in ionization energy is going to be much greater. Let's say 500. So if this was plus 100, this is going to be plus 300, and you're going to require 500 kilojoules per mole. So that's one thing to remember. When you jump shells, when you change energy levels, there is a significant change in the ionization energies, and you can usually tell the valency of an atom or an element by looking at its successive ionization energies, and wherever you notice a significant difference is where you know that you dropped an energy level down, or the energy level decreased by 1 and we came closer to the nucleus. So yeah. Now let's talk about the group trend. So the group trend. Here we won't concern ourselves with successive ionization energies. We're just going to talk about first ionization energies and how that varies as you go from the top to bottom in a group. So yeah, and the trend is that it decreases as you go from the top to the bottom of any group. So yeah, and here's why. Let's look at a couple of examples. Let's look at, for example, group 2. Let's look at beryllium, magnesium, and calcium. So beryllium has 4 electrons, so stable duplet. There we go. And I'll just copy this. And magnesium has 12, so duplet and then 10 more. So these are 8. And then you need what? And then you need 2 more. So this is beryllium, this is magnesium, and then calcium, you need 8 more than this. So this is how many? This is 8, 16, 18, and you need 2 more. So I'm just taking the first 3 elements in group 2 as an example. So now if you look at these, you'll notice that the outermost electron is so much closer to the nucleus than here, and here it's even farther. So as you go down a group, the distance of the outermost electron from the nucleus increases. इसका मतलब जैसे हमने यहाँ पे पढ़ा था, as the distance from the nucleus increases, the shielding effect is also going to increase, and since the effective nuclear force on that is decreasing, हमें अपनी energy कम लगानी पड़ेगी in order to remove that outermost electron. So as a result, ionization energy, so first ionization energy decreases down a group, and this is why, because you get farther and farther from the nucleus, experience a greater shielding effect and a smaller effective nuclear force. So yeah, let's talk about period trends. So let's again take an example, and this time let's consider period 2. Period 2, we'll consider the first 3 elements of period 2. We'll have lithium, which has 3 electrons. So 1 here, this, and we'll just keep adding electrons. So that was, and then beryllium has 4 electrons, and there we go, that is boron. So this is lithium, beryllium, boron. Immediately you should notice a difference between the group trends and the period trends. In the group trends, the size of the atom was increasing. and the distance of the outermost electrons from the nucleus was increasing as well. But here you can see that, for example, if we consider this to be the outermost electron, this is a distance, and this is the outermost electron, that is the distance, and this is still the outermost electron, and this is still the distance. So the distance is remaining constant. But here, if we say how many protons does this nucleus have, we say that it has 3 protons. Here it has 4 protons. Here it has 5 protons. So the number of protons is increasing. So the effective nuclear force is increasing. Sorry, the nuclear force is increasing because protons are increasing. The shielding effect, however, remains the same. Shielding effect is constant. And why? This is because we're not changing energy levels. The distance from the nucleus remains constant, as you can see in this example. So as a result, shielding effect constant रह रहा है, nuclear force बढ़ती जा रही है. That means this electron, well, I'll highlight here, this electron is being pulled to the nucleus with a much stronger force than this electron. और इसकी वजह से the first ionization energy of this will be much greater than this. So yeah, because this is experiencing a greater nuclear force and this is experiencing a relatively lesser nuclear force. So as a result, the trend turns out to be the first ionization energy across a period increases across a period. Now there are a few exceptions to this. Let's see. The exceptions are, and if you look in the note, you'll find this graph. I'm just gonna draw, I think, a rough approximation of it. I'm not gonna label it perfectly or anything. And it goes like lithium. You start off with lithium, then there's a drop after beryllium, then beryllium to boron is the drop, boron to carbon to nitrogen, then NO, there's a drop, and then O to F, and then fluorine to neon. So the exceptions that we come across are these. So you know how we said it increases across a period. So here it's increasing, it's generally increasing, but there are 2 drops that we're concerned about, and these are the exceptions. So I'll label these. This is from beryllium to boron, and this is from nitrogen to oxygen. So beryllium to boron तो हमने draw किया था, तो हम उससे ही समझ सकते हैं. I'm gonna clear a bit of this so that we can have more space to work here. So we are going from beryllium to boron, and the ionization energy is dropping instead of increasing. So why is that? This is because if you consider the quantum mechanical model, and we're gonna draw it here. So this is for beryllium, and this is the nucleus, and this is 1s, and it has 2 electrons in 1s, and then it has 2s, and then 2 electrons. So how many? So there you go. You have 2 electrons here, 2 electrons here. That is the entire electronic configuration of beryllium. If you were to draw the same thing for for boron, this is still the nucleus. I'm just not going to label it again because you should know this. 1s, 2s, and then you have 2px, 2py, 2pz. And this is 4 electrons, boron has 5, so there's only 1 electron here. And so if you look at the outermost electrons and we compare them, for example, this is the outermost electrons in beryllium, and this is the outermost electron in boron. And as you can see, the outermost electron in boron is much farther from the nucleus. It's in the 2p orbital, which is farther from the nucleus, as compared to beryllium, whose outermost electron is in the 2s orbital. and is closer to the nucleus. So therefore, this experiences a greater shielding effect, and hence requires less ionization energy to remove. And that is why the ionization energy actually drops, because the new electron enters a new shell, it enters the p orbital, which is farther from the s orbital, while the outermost electron in beryllium exists in the s orbital closer to the nucleus. So that's justification for the beryllium to boron exception. What about nitrogen to oxygen? So now if we draw out again the electronic configurations of these two atoms, so if you have nitrogen, and nitrogen has 7 electrons, so we'll just draw this. So 1s, 2 electrons, 2s, 2 electrons, that's 4 electrons. We have 3 more electrons, so 2px, 2py, 2pz, 1 in each. And I'll just duplicate this. This is oxygen. Oxygen has 1 more electron, and that's where it goes. I'll just draw it in yellow so it's more clear. Now, the reason ionization energy drops from oxygen, so ionization energy drops going from nitrogen to oxygen, is because of this 1 electron. So remember I talked about electron-electron repulsion before? Well, it happens here as well. As you can see here, all the 3 electrons are in different shells, so they're at a maximum distance from each other. However, these 2 electrons are close together, so they repel each other. And this repulsion decreases the amount of energy that we have to put in, because it basically helps us extract the electron. Because, for example, this electron is already pushing this electron out of the atom. It's trying to push it out of the atom. So, हमें कम मेहनत करनी पड़ती है, and we have to put in less energy, which is why the first ionization energy of removing this outermost electron is actually less in oxygen as compared to removing any one of these 3 electrons that are equally distant, that are in equal distance away from the nucleus and are at a maximum distance from